if we want to start using electricity to do useful tasks, we need to use some kind of electrical potential energy. Also something called potential difference is how we usually describe this electrical energy. So we have something called electric potential. And the electric potential has a very specific definition. We'll define it in terms of an equation. Change in V is equal to the change in electrical potential energy, all divided by charge. So electric potential is the energy you get out per unit charge. And this delta stands for a standard, it stands for a difference. So delta V is equal to the potential, which is the energy per charge at some point B, minus the potential at some other point A. This is the change in potential to move a charge between 2 points. And when you do this, you can actually define a new kind of unit as well. So when you send a charge through a potential difference, so when I'm sending a charge through some V, I get something. I can define this new unit, something called an electron volt. So that's a charge being sent through some kind of voltage, some potential difference. This is equal to 1.6 times 10 to the negative 19 coulombs, the fundamental charge, multiplied by 1 volt. So in taking a charge, that's the fundamental charge, so basically an electron, we take the absolute value of that to get the electron charge to be positive, and we send it through a potential difference that's going to be equal to this thing called 1 volt. And this is going to give us some kind of energy. We have some energy, 1.6 times 10 to the negative 19 joules. So if we're going to use potential, this potential V, to accomplish some task, the task we're doing is going to use some energy divided by some amount of charge that's being used to accomplish this task. Now the common place that you'll see V, so you'll see potentials. Well, we can look at the units of this potential. Units of electric potential are going to be something called volts. And the place where you're probably used to seeing this is with batteries. They're labeled in voltages. And that voltage that you get is the energy that the battery has stored per unit charge inside of the actual battery. So it's kind of like the energy. It's just kind of scaled to the charge that you have. We can also get potential, electrical potential, through not just using charges. We can also get it through electric fields. So we've talked about electric fields. And if we want potential from an electric field, the potential between two positions inside of an electric field, so we'll say V between points A and B inside of an electric field, is equal to the electric field times D. Okay, where D is the distance between points A and B, and E is a uniform electrical field. The typical place we'll see this is between two plates. So maybe I put some charges on a plate, and I have some charges on another plate, some negative charges. That creates an electrical field. The electrical field goes away from positives and towards negatives. So this is an electrical field that I'm creating between these two plates. And the potential that exists between these two plates is going to be based on the size of this electrical field and then the separation of the plates, how far apart they are from each other. So maybe this is all the charges on plate A, and this is going to be the charges on plate B. Okay, so it's one way that we can write potential. due to an electrical field. We can generalize this a little bit so that it works in more than just this little parallel plate kind of situation. So we can generalize this to a definition of an electric field, where an electric field is equal to negative change in a potential divided by a change in position over which that potential takes place. So again, the V is the potential, which is the energy per unit charge, and the delta S is the change in position over which that potential takes place. So that's a change in position. And when we're applying electrical potentials, we're usually trying to move charges over some distance, and that delta S is the distance we're moving. Something to note is that the electric field is going to act in the opposite direction to the electric potential. We get that from that negative sign that comes out front. So these are two good definitions. V equals ed for potential between a couple of plates, and E more generally is equal to the negative change in potential divided by a change in position over which you're having that potential take place. Now, you don't just have potentials due to electric fields. You don't have it just due to charges. You can actually create an electric potential from just a single charge. And we can denote that by V, the electrical potential of a single point charge, is K, the same constant as before, where K is 8.99 times 10 to the 9, times Q, however large your charge is, divided by R, how far you are away from that charge. So every charge is going to create an electric potential at every single point. And that electric potential depends on K, Q, the size of the charge, and R, how far you are away from that charge. So if I have a big charge Q right here, it's creating some electrical potential at this point, and that's related to that little r, how far you are away from that point. If I move farther away, then the electric potential is going to be slightly less because you're going to be at a higher distance, so your potential is going to decrease. Now, an awesome point to recognize is that potential is different than the electric field because it's a scalar. So that means we don't really have to worry about direction. So if we want to find potential differences, we can just add them up for various different charges, and we don't need to break into X, Y, and Z directions. So if I have a whole bunch of charges, I have a Q here, maybe another Q, maybe another Q over here. The electric potentials all depend on how far you are away from this point, from these charges that are creating your potential, but I don't have to break it up into components. I don't have to break into X and Y directions, which you will have to do or have had to do with the electrical fields. So directions, the direction, X, Y, or Z, for the electric potential, that doesn't really come into play. Direction doesn't matter. You can straight up add these numbers. And that should make sense when we think about what the electric potential is. The electric potential, again, its most basic definition is basically the energy per charge. And if we think about what energy is, energy was a scalar as well. It had no direction. So it makes sense the potential has no direction either. So we can further understand potential by thinking about it in terms of other kind of electrical quantities we've talked about. We know about electric fields. We also know that potential has lines that are associated with it. So we can write down the equation for electrical potential due to a point charge. V is equal to K times Q divided by R. So I can write down my charge. Here's my positive charge. I can write down the field lines. The field lines for this all point away from this charge. Remember, electric field goes away from a positive charge and towards a negative charge. So I'm just drawing a few lines pointing, we use the phrase radially outwards from this single charge. And what I can do with this is I can figure out what the potential is. If I go a certain distance away, let's say that distance is R1, then I have a certain potential. And it doesn't matter which line I go along, as long as I go around that same distance. So if I go R1 down, I have that same potential. I can go R1 over, I have that same potential. And as long as I'm the same distance away from my central charge, the potential is not going to change. So I can draw a nice little, I can think about it being a circle. So as long as I'm on this circle, I'm always the same radius away. And I can draw another line that's a little bit further away, so a slightly bigger circle. But if I draw this circle, I am the same radius away from my central charge, so that means I have the same potential. So each of these colorful lines have a specific name. These are called equipotential lines. They are concentric circles around your central point charge that creates your potential. Okay. There's some rules for drawing these equipotential lines. The equipotential, it depends on your distance from your charge. As long as you're the same distance, you have the same electric potential. And if you look closely, you'll see that this is drawn in concentric circles. So a circle gives you an equipotential. And we'll also notice that at all points, the equipotential has a specific angle relative to the field line. The equipotential is perpendicular, so it's at a right angle to your field. And we can see that in our picture. So here I have my equipotential line, and I have my field line. If I draw the angle there, that's 90 degrees. So I've got my field line going up, and at this point, my equipotential line is going left and right, so I have that 90-degree angle. And I can do any of the field lines. I have my field line going kind of off at an angle. So there's my field line, there's my equipotential line, and if I draw the angle there, it's going to be 90 degrees. The equipotential line is always perpendicular to your electrical field line. Now, our modern society is based largely on using electricity, so we want to know how to actually use and access this electric potential and this electric potential energy, more importantly. Our modern life kind of depends on this. So how do we access it? How do we store it, and how do we use this energy? Well, there's a device that we've created that's called a capacitor. And a capacitor has the ability to store charge. And this has made our lives much, much easier. So how much charge can you store in a capacitor? Well, it depends on V, your voltage. Depends on your electric potential. Which again, remember we describe with this word voltage. It's the number you see written on your batteries. And the physical aspects of the capacitor. Something we'll call C. Okay, so the amount of charge we can get depends on the voltage and the physical aspects of the capacitor. We'll label this with a C. We'll call this the capacitance. And the capacitance that you're going to have is going to be based on what you make your capacitor out of. It can be based on the size of the capacitor or the geometry, how you set it up, how you create your capacitor, and the kind of materials that you make your capacitor out of. And since this is physics, we love equations. The equation we're going to use to describe this is the capacitance of something is equal to the amount of charge that you can store, all divided by the voltage that can be applied in charging that capacitor. So this is what your book likes to use, what most books like to use for describing capacitance. I like the Home Shopping Network, so the equation I like to memorize is Q equals VC. This is easier for me to memorize. My mom always used to shop on QVC, and it's the same equation. It's just reshuffled around, do a little bit of algebra, and you'll see that these are equivalent. Okay, so let's talk a little bit about the sizes and geometries of these capacitors and how that comes into play. One of the most common ways that we can store charge is with something called a parallel plate capacitor. So this is basically two sheets that we take, make it out of some conductors, so these conductors can store charge. And we put them in arrangement so that they're parallel to each other. So we have two parallel plates. Each of these plates has some size, some length times width. We're going to call A. That is the area of your plates. And they're separated by some distance d. Now these two parallel plates, we can describe their capacitance based on the material that they're made out of and the geometry of the situation. So the capacitance of these two plates is going to be equal to A, which is the area, times epsilon naught, which is something called the permittivity of free space, divided by the separation, d, how far apart these plates are. So we can use this to make parallel plate capacitors. And if I want to make my parallel plate capacitor a little bit more useful, I can actually put some stuff in the middle of it. So instead of being empty space or air, I can insert some material. If I start inserting material into this parallel plate capacitor, my capacitance is going to change. My capacitance is going to be equal to the Greek letter kappa, which is like a kind of weird looking K, times the area times epsilon naught, all divided by d. And this kappa is something called a dielectric constant. So this is a capacitor with parallel plates when you insert some material in between it to kind of adjust what your capacitance will be. If you don't have any material, this is the equation you'll use. If you do have some material that you're putting in to change your capacitance, then you can use this dielectric constant, this kappa. It would be a constant that's usually found or looked up inside of a table. So that's one way that we can physically create capacitors using parallel plates. Now the real purpose of a capacitor is to really use energy. And to use energy and release it in the amounts that I want, I need to be able to adjust my capacitances. Okay, so I need a wide variety of capacitors. I might need 5 capacitors that have a strength of 5. I might need capacitors that have a strength of 10. And I might need capacitors that don't exist, that don't have a value that actually exists. So I need to be able to get any capacitance that I want. And there are 2 ways to combine capacitors to change the total capacitance that I get out. 2 combinations, 2 ways that I can combine these capacitors. I can combine capacitors in something called series, and I can combine capacitors in a shape called parallel. And by combining capacitors, I can get out any capacitance that I want. So in series, if I take capacitors, I just hook them up one right after another. So I'm going to draw some circuit pictures. I have a little wire that comes in, and then 2 parallel lines, and that represents a capacitor inside of a circuit diagram, which we'll be working with as we move further through physics. So I'm going to draw 1, 2, maybe 3 capacitors. So I have these 1, 2, 3 capacitors, one following right after another, and I need to add these up and figure out what the total capacitance is. So by combining these together, I can add them up and combine them into one total capacitance. I'll call that C total. So this is a way that I combine capacitors that I can buy to get a final capacitance that I want. And when I do this, when I add capacitors in series, I can do 1 divided by C total. The total equivalent capacitance from adding these together is equal to 1 over C1 plus 1 over C2 plus 1 over C3. If I had additional capacitors, I would just add those on, plus 1 over C sub n, all the way up to however many capacitors I had. Now in this situation, I only have the 3, so we'll just worry about those 3 capacitors. And now let's say I'm given values for these capacitances. C1, 2 farads. C2, we'll say, is also 2 farads. And let's say C3 is also 2 farads. They don't have to be. I could have a variety of different numbers, but those are just the ones that I picked to throw in here, so I can toss those into this equation. So 1 over C total is equal to 1 over 2 plus 1 over 2 plus 1 over 2. So I've plugged in these values of 2 for all my capacitances C1, C2, and C3. I add these up, and I get a value of 3 over 2. So 1 divided by C total is equal to 3 divided by 2. Now I need to find what C total is. So I need to do some algebra. I need to kind of solve this for C total. Right now I have C total on the bottom. I want to get it to the top, so I can cross multiply it over. So I multiply both sides of this by C total. So my C total cancels on the left-hand side, and I end up with 1 equals 3/2 times C total. Now I want to get C total by itself, so I need to multiply this side by 2/3. Multiply one side, I have to multiply both sides. So if I look closely at what I'm doing, by multiplying by 2/3, I'm canceling these 2's, I'm canceling these 3's, and on the right-hand side, I end up with just C total. And on the left-hand side, I end up with 2/3. So I've taken 3 capacitors. Each one of these has 2 farads, and I've decreased the capacitance down to 2/3 of a farad. Now, another way I combine capacitors is if I combine them in parallel. Now, in parallel, I have a wire that comes in, and it can split. It can choose 3 different paths. So I could go through the first capacitor, I could go up and go through C1. I could just keep going straight. I could go through C2, or I could go down so that I went through C3. If I could combine my capacitors like this, this also gets me down to a single total capacitance, C total. But since these are in parallel, they're going to combine a little bit differently. So we use the same capacitances, C1 equals 2, C2 equals 2, and C3 equals 2. But if I'm in parallel, the capacitance adds a little bit differently. It's actually a little bit easier. So C total, if I'm in parallel, is just the combination of all the capacitances. C1 plus C2 plus C3. There are no fractions involved here. So I like to think that adding capacitors in parallel is a bit easier. So I get 2 plus 2 plus 2. So my total capacitance when I set up my capacitors in parallel is equal to 6. So if my final capacitance is greater than my individual ones, I'm adding in parallel. If my final capacitance wants to be less than my individual capacitors, I want to combine them in series. So these are 2 ways that you can combine capacitors to get out any kind of capacitance that you want. But now I want to know how much energy is stored inside of these things, inside of a capacitor. There are a variety of equations that we can use to calculate the energy in a capacitor. Energy in a capacitor is equal to charge that you have times the voltage that you have divided by 2. But I can recognize that there's an equation for capacitance if I want to know how much energy I have inside of a capacitor, where Q is equal to V times C. So I can take this Q and I can plug it in right here for my Q and my energy equation. So now I know that my energy is equal to V times C times this V all divided by 2. So all I've done here is I've taken this Q, I've taken that Q is equal to V times C, and I've plugged it in. And when I do that, I can solve this out, and I'll see that E is equal to V squared times C over 2. So this is another equation that I can use for capacitance, for energy inside of a capacitor. But there's yet another equation I could use. I could also use E is equal to Q squared over 2C. And I've just derived this. I've plugged and chugged some of these other equations in. So I'm getting rid of V. So here all I've done, I found V is equal to Q divided by C. And then where I have my V here, I plugged in Q over C to get this final result. You should kind of do that at home and make sure you can do that kind of algebra step. All of these things, these are all the same equation. They all represent the same thing. They all let you solve for the same values. It just depends on what variables you want to use. And you should be able to do this kind of algebra at this point in a physics course. And that's basically electric potential energy, and capacitance.